Principal Component Analysis, or PCA. Principal component analysis is a dimensionality reduction technique used to transform a high dimensional dataset into a lower dimensional one by identifying the directions, which is the principal components, that capture the maximum variance in the data. PCA is widely used for data visualization, noise reduction, and speeding up machine learning algorithms by reducing the number of features. Let's go ahead and implement this using scikit-learn and running through line by line in Python. So I'm going to go ahead. I've already created a file. I'm going to say import necessary libraries. In this particular case, I'm going to first from sklearn.decomposition import PCA, which imports the PCA class from scikit-learn's decomposition module. Now, PCA is dimensionality reduction technique that transforms data into a lower dimensional space by identifying the directions which are principal components that capture the most variance in the data. Next, import numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulation in Python. Next, let's go and get some sample data. This time I'm getting points in a 3D space. X equal to np array, which defines the feature data x as a numpy array where each sublist represents a data point in 3D space with three values x, y, and z coordinates. For example, 1, 2, 3, and 5, 6, 7 are 2 points in 3D space. The shape of x is 5, 3, meaning there are 5 data points with 3 features each. Next, go ahead and initialize and fit the model. So first, PCA equal to PCA and components equal to 2. This initializes a PCA model with the following parameters of n components equal to 2, which specifies the number of principal components which are dimensions to keep. Here, n components equal to means we are reducing the data from a 3D to a 2D object. Next, we will going to say x reduced equal PCA.fit transform x. This fits the PCA model to the data x and transform it into a lower dimensional space. The fit transform both fits the model, finding the principal components, and transforms the data based on these components, resulting in x reduced, which has a shape of 5, 2. Now let's go ahead and print the reduced data and print the explained variance ratio for this. Now here, x underscore reduced prints the transformed data in the reduced 2D space. Now each row in x reduced represents a data point in 2D space where each value represents the projection of the original data onto the first and the second principal components. This one, the second one, prints the explained variance ratio, which indicates how much of the total variance in the original data is captured by each principal component. The function PCA dot explained variance ratio underscore is an array where each value represents the proportion of variance explained by a principal component. This information is helpful for understanding how much information is retained in the reduced dimensional representation. So let's go ahead and run it in our command prompt. I'm going to clear the previous one, and I'm going to say here, make sure it's saved. Say Python principal, and you'll see the reduced data is these are the coordinates based on the reduced data, and the explained variance ratio is 0.99, 0.00. So this code demonstrates how to use PCA to reduce the 3D data set to a 2D while retaining as much variance as possible. The explained variance ratio shows the contribution of each principal component to the total variance, providing insight into the effectiveness of the dimensionality reduction. If you had any questions or issues implementing this, let me know and I'll get back to you.